Okay, so you roll 3 6-sided dice, and we're trying to work out what's the probability they're all different numbers, which, on the face of it, not so easy. But if you know how to break it down, you can break it into simpler parts and figure it out that way. Let's see what people said. And we should get a fun word cloud over here. Okay, so we got some answers like 5 out of 6, 4 out of 6, 5 out of 9, 120 out of 216. So some nice big numbers here, very nice. Let's see if we can, what's the biggest words here? Would. What would you do? I guess that's on me for would. Probability, also very, very big. Multiply, outcomes. Let's see, any other cool ones? Denominator, oh, that's fun. Numerator, okay, these are cool. First, we do something. Oh, 6 cubed, that's cute, okay. Oh, I like this one, 6 times 5 times 4. So we got some good stuff here. Some people are writing out some actual solutions. Let's see, did anybody write tree? That's one possible thing you could have written. Tree, I don't see tree. There's a tree in the bottom. Top right, there's a tree. Oh, over here, oh, it's actually quite big. Oh, amazing, look at that, it's just sideways. There you go, so probability tree, which maybe is this probability, is one major way to do it. And in fact, almost all the problems in this class can be done by probability tree or by another method. But probability tree sort of catches a lot of the things. Let's start a new one today. So that's one method is probability tree. Probability tree. Okay, that's option 1. And that's always a good one to try if you're kind of stuck. You're like, how could I break something down as a probability tree? Another one, I saw things like 6 times 5 times 4, which looks like this is a formula that we've seen before. When you start with a number and you start multiplying down, this is the falling factorial. This is 6 falling factorial 2. And so this was related to our discussion of combinations and permutations. I think this one is the permutation, in quotes. So again, counting, aka counting objects where order matters. Counting with order. Okay, and this is I would say this is option 2. And both of these can work. They're both equally good and will get you there. I'll give you an option 3, which does not work. Option 3, don't do this. Will not work, but is a good try. So one thing you could try to do is count ways that things could go together. So you could say like, count doubles and triples, and this will turn into a hard problem. So sometimes in probability, you have multiple ways to do it, but some of them are a lot of work. Maybe I should say it instead of will not work. Maybe that's too pessimistic. Will be extra effort. Will be extra effort. So if you try to sort of do it the classical way, you're like, what's the probability of rolling doubles? What's the probability of rolling triples? You're going to get into a whole thing. It will eventually work, but it will be extra hard. But I'd say those are the 3 ways to do it. And the probability tree or the counting are both very, very nice ways to do it that will get you the right answer. Let's get into some of these, but maybe I'll go into the tree and see, or the word cloud and see if anybody said anything else. Oh, that's a good question. Let's see if somebody wrote something here. So some people wrote probability tree. Yeah, let's see. 6 times 6 probability tree. Yeah, lots of people said probability tree. They're very nice. Okay. I wonder if anybody wrote falling factorial. I guess not. Multiplying probability tree. Oh, factorials, etc. Very nice. Okay, great. So it has been pointed out to me that there is an error somewhere on what I have written. Does anyone see what is the error on the thing that I wrote? Yes. Yes, it is. It should in fact be something else. Do you know what it should be? 6 falling factorial 3. Very nice. Yeah. And that's because there's 3 things in the thing. I think I got mixed up because we're subtracting 2. The smallest thing is 2 less than the starting thing, but there are 3 terms, and so that's what we're doing. Okay. So let's do one of these 2 ways. I guess I will let you guys do a hand vote. Which option should we see first? Who would like to see option 1, the probability tree? Only a few people, maybe a little handful. Option 2, the falling factorial. Most people want to see that one, so let's do it that way. So we'll do it both ways, but we'll start with option 2. And so this is what we're going to do. The probability of all 3 dice are different. And again, you could give this a name, or you could just describe it in words, and as long as it's clear what you mean. We're going to use this formula. It's the number of ways to get a sequence of length 3 with 3 different numbers. Numbers where they are all different. So 3 different numbers, 1 to 6. Let's say 1 to 6, divided by the number of ways of any sequence of length 3. Okay. So same numbers, 1 to 6. And the reason this works is because all of the outcomes are equally likely. So if you were going to go in more detail, you would have to explain this works since all outcomes are equally likely. Since all sequences are equally likely. If it was an urn or something, and you're pulling the numbers out of an urn or a deck of cards, you're doing it with replacement versus without replacement, this would not be true. But in this case, for rolling dice, it is true. So that's very nice. So that's the first bit. And again, you could spend a lot of time justifying this, but this is kind of a short version of the justification. And now you have to count these 2 things. This top one is very similar to a homework question that you have that's due today on the number of passwords you can make on a safe, where that has different numbers. And this one is counted exactly by the combinations with order, also known as the permutations. And this one is exactly the number of ways, all different, is exactly this 6 following factorial with 3 terms, 6 times 5 times 4. And that is because there are 6 ways to choose the first number. For the first number, there's 5 ways for the second number. And the reason it's only 5 is because the first number is forbidden. Whatever you chose in the first slot is not allowed to be picked in the second slot. And last but not least, there are 4 ways for the third number because the first 2 are forbidden. Okay. So 6 times 5 times 4. And the number of ways in total, NE, is 6 times 6 times 6, also known as 6 cubed. And that's because there are 6 choices for each slot. All have 6 choices. So there's no restrictions. So all of the numbers 1 to 6 are all equally good. Okay. So the final answer, the probability of all different, is 6 times 5 times 4 divided by 6 times 6 times 6. And these have some nice cancellation. Let's see. 4 has 2 2s in it. So I could cross out this 4 and replace these with 3 times 3 to get 5 out of 9. And so that is the final answer. It's 5 out of 9. Just over a 50% chance that when you roll 3 dice, that they will all be different. Very close to 50%. Yeah? Yes. So the way you're doing it is the probability tree way. We'll go over this way in a second. And it's equally good. And it really is the same thing. It just is a personal preference on what you prefer to try. In this case, they both work. In some problems, one will work a lot better than the other. In this problem, both are pretty good. Yeah, we'll do this one very quickly in 1 second. Any other questions or comments about this counting way of doing things? Okay, let's do the probability tree way. And I will do it a bit quicker because we've already seen one way. And I really think of it as imagine rolling the dice one at a time, and just you either thumbs up, they're all different, and you can keep going, or boo, you have a duplicate and you lost. So so keep track of progress as we roll the dice one by one, as we roll the dice one by one. Okay, and so when we roll the first dice, 2 things can happen. Either we have at least 1 duplicate and then we lose, duplicate, roll or keep going. And we're going to start here. And the thing is, when you roll your first dice, no matter what happens, it's going to be fine. So you're going to keep going 100% of the time. 6 out of 6 possibilities will lead you to keep going. Your first dice roll is kind of a freebie. That one will be fine. After that, that's where things get interesting. Because after your first dice, there is only a 5 out of 6 chance you will keep going on the second dice roll. So you could sort of label these columns as the first dice, the second dice, and the third dice coming up. And this one has a 1 out of 6 chance of a duplicate roll, because whatever you rolled on the first dice, you have a 1 out of 6 chance to copy that one. And then, last but not least, the third dice is the last one. Finally done, all different. And you have a duplicate roll. That happens with probability 2 out of 6 now, and a 4 out of 6 chance to keep going. And again, these 6 out of 6, 5 out of 6, and 4 out of 6, these are actually conditional probabilities. 5 out of 6 is the conditional probability that the second dice will be fine, given that the first dice was also fine, and so on. And when we have these probability trees, we know, we're used to it now, you multiply along the branches. So you multiply along this branch. So the probability of the event that we're looking for, the probability of all different, will be the product 6 out of 6 times 5 out of 6 times 4 out of 6, which is exactly what we got before. So same answer, slightly different reasoning, equally good way to do it. The probability tree way, I think, is in some ways a little bit more flexible, because if it's like an urn problem and funny things are happening, if balls are getting added to the urn and so on, you can mess with these fractions a little bit more. The combinatorics way is also kind of more useful in other ways too, if you have some funny problem about sequences. So they both have their pros and cons, and it's good to know both. In fact, you should know both, but this one can be done either way. Okay, questions or comments about that way of doing it? I do have a quick question for you all, which is, this problem is secretly very closely related to a problem we did very early on in the course. What problem is this actually like? What problem is this similar to? Does anyone know what problem this is similar to? Yeah. It is the birthday problem. This problem is exactly the same as the birthday problem. The birthday problem, which is, the birthday problem was how many people need to enter a room before 2 people have the same birthday. Another way you could say that is, if there's 10 people in the room, what is the chance that they have the same birthday? And the only thing that you have to replace is a 6-sided dice that becomes 365 days in a year. So remember, we were assuming that everybody's birthday is independent and has a 1 out of 365 chance to be any given day of the year. That is exactly like a dice roll. So a dice roll, the dice rolls are independent, and they have a 1 out of 6 chance to be any of the sides. So if you replace people's dice rolls with birthdays, a 365-sided dice, that would be the same thing. And the 3 dice you roll is the number of people in the room. Number of people in the room. So essentially what we calculated is, if there were 6 days in a year and 3 people were in the room, what is the chance that they all have different birthdays? We just calculated that. In real life, there's 365 days in a year, and you should put like 20 people in the room or something to get an exciting result. And so in fact, if you do it with 23 people in the room, if you calculate it out, it is approximately, let me not do approximately, let me say, this goes to the probability of all different birthdays is just under 50%. It will be approximately, I think it's like 49.5%. So with 23 people in the room, if you work out the same kind of calculation, the chance that they have all different birthdays is slightly less than 50%, and that means the chance that somebody shares a birthday is slightly over 50%. You only need 23 people to have a 50-50 shot at a shared birthday in the room, which is kind of a cool counterintuitive thing. You kind of think it should be more than that. Okay, any other questions or comments about this one? Okay, I think that's where we're going to stop this example problem. We're going to see some more other example problems and some discussion about Venn diagrams and what is a Venn diagram and what isn't.
again. This is what it does. And I want to put this one up. And let me just make sure that this is showing what I want it to show. It isn't. Should be good. Oh, come on. Come on, come on, come on, come on. Oh, irritating as sin. Just a second.
Do you want it to duplicate, or do you want?
I want it just to show that freaking slide. This is such a piss off. Oh, okay. Oh, this is such an irritant. Okay, just a second. I'm going to do this. Gonna try again. How we doing? There we go. Okay, that'll do. Okay, couple little miscellaneous things here. What I want to do for the remainder of the class is not necessarily solve problems in their whole, but to give you a couple hints on how to attack some problems. Sometimes, so there's a lot of problems that there's a solution that's very long, but there's another solution which is very short. If you are working on a test problem and it is like just bogging you right down, it is probably because you have not found the fast way to do it, okay? So you're looking for efficiency. Anyhow, a couple of asides. One is this one here. Dr. Jeremy Balka teaches STAT1200. I'll be teaching it this winter. Almost all of you will be taking that in the winter. He has but a single thing on his door, which was his own creation. It was a Venn diagram. Well, technically an Euler diagram. Discussions that are not a waste of time, and discussions about the distinction between Venn and Euler diagrams. Let's look at those two events. Are those independent events? Who says yes, they are independent events? Who says absolutely not? Why not? Yeah, they're mutually exclusive events, right? And this was the point he makes, is that in his view, it is a worthless discussion about the difference between Venn diagrams and Euler diagrams. We use the terms interchangeably, okay? So what is the difference between a Venn diagram and an Euler diagram? Venn always drew all the intersections, even with empty intersections, whereas Euler would collapse it. So for example, if A was a subset of B, proper subset of B, Euler would draw it as a circle within B, a circle for A within B. We do that all the time. So technically, we often do Euler diagrams instead of Venn diagrams. But we'll call them Venn diagrams
That's
anyhow.
right. You just call them blobs.
Call them blobs, yes.
Then nobody can get mad at you.
Okay. So another thing is this diagram. This was one I searched one time on, I don't know, I just wanted to see what Google would say if you just searched for independent events. And it came out with this, which this is okay. And it had this picture to illustrate independent events. Is anybody outraged by that?
Yeah, I think you are.
I was outraged. clearly those are not independent events, they're mutually exclusive events. The weird thing is, and this is one of the things you got to watch with things like artificial intelligence, is that they'll sometimes just grab weird things and take it totally out of context. In fact, if you went to the place where they had got this diagram, something called Wise Ant, which was kind of cool because it's named after ants. They actually had this as an example of non-independent events and mutually exclusive events, but Google search engine, whatever it did, just reached in and grabbed this diagram and said, the article's talking about independent events, so this will work. Boom, toss it in. So you got to be very skeptical. You're always skeptical to say to yourself, is what you're being told makes sense? So I got to come back. I'm going to just mention when Professor Nika had the falling factorial, 6 and 2, how many of you said, I don't think that's right, I think it's 6 and 3? How many of you felt that? There's a bunch of you. So why didn't you not say anything? Because you're saying, I shouldn't question that. No, you should always question things, okay? And we will make mistakes up here. He will make much fewer than me. And partly it's like your brain is thinking ahead of what you want to do next, so you just kind of, sometimes the hand does weird things. But you want to question, so I'm going to set up another protocol. We'll see if Professor Nika likes this one or not. Sometimes we don't see that you've got a question, so what we want you to do to draw our attention, knock, okay, and make sure we get your attention on that. So, question things that don't make sense to you, okay. So the next thing I want to do is, let me just do something for a second here.
I don't know if the freezes will work. Hold on.
You don't know if the freezers work?
Move the mouse around or something, or go back and forward.
It looks like it's frozen.
Okay, I would say 50%. Let's find out.
Okay, I want to go back now.
You see, this one is frozen and that one's not frozen. Exactly 50%.
Okay. So I haven't posted these yet. I'm going to post these up, but I wanted to bring up something here. This is very straightforward, and then there's answers. Those shouldn't be easy. There's another Bayes theorem question involving. Hey, just a second. Just a second. Oh, I know what's going on. There's another Bayes theorem question involving. Well, this is very sensitive stuff to discuss. Maybe I won't even. They're trying to find the probability of the father of the calf. They do not know. Oh my goodness, this is so shocking. Anyhow, you can try that question. It's a basic Bayes theorem question. Should be straightforward there. But here's the one I want to discuss a little bit here. This question here was extending the idea of like 2 urns up to 3 urns. And Professor Nika gave, oh my goodness, what did I forgot to take my pens out. Okay, got my pens, just a second.
By the way, a very valid question you might have is why do people care so much about urns? What's the obsession with urns? Well, the urns are supposed to be models of populations. So instead of having 3 red, 2 white, and 5 blue balls, you should imagine a population that has 300 people that have a disease, 200 people that are immune to the disease, and 500 people that are susceptible to the disease. So the urns are stand-ins for any time you're pulling things from a population. That's why we care about them so much. But it's more fun to talk about urns. This is good.
And it also clarifies certain structures of, get a very clear structure that this is exactly what is happening. And then when we go into our real populations, there's a little bit of fuzzy things. Does a person have the disease or just the symptoms? And, there's some aspects that make it fuzzier when we deal with real populations. And that is the quote from Dr. George Box that Professor Nika mentioned before. All models are wrong, some models are useful. The idea being that we come up with a model that technically is generally not perfect, but it's very useful. It's a useful device. It's going to get our probabilities, for example, sufficiently close to be useful for us. Okay, so I wanted to mention this question here. Urn 1 contains 3 red, 2 white, and 5 blue balls. Urn 2 contains 1 red, 4 white, and 5 blue balls. And so you've seen something similar to this for setting up the Venn-like diagram. And, you can attack that with a probability tree. You could attack that with a probability tree. And, let's just see, just for that first ball, let's see, we got 3 different urns we can pick from, and then we've got 3 colors. And so that's 3 times 3 for each of those branches. So we're up to 9 branches. And then if we pick a second ball, we've got, we're up to 27 branches. And maybe if we picked a third ball, we're up to 81 branches. So these things can get very bushy on you. And what you always want to do is just kind of like think of simplifying the problem. Okay? So in this particular case, an urn is selected at random. 2 balls are randomly selected with replacement. What is the probability that both are red? Well, you might say to yourself, okay, I might get, I could get 2 reds from any of the 3 urns. Again, it's done with replacement. Oh.
I have a problem.
You have a problem.
I don't think you can get two red from any of the 3 urns.
You don't think I can get 2 reds from any?
No.
Why not?
Well, urn 2 only has 1 red ball.
I said I'm sampling with replacement.
Oh! I take it back. Thank you for clarifying.
Yeah.
Very good.
Would have been a good problem without replacement.
That would have been really exciting. Yeah. Okay.
Yeah. Which could still be done. The problem. Anyhow, so if you're looking at it and you start saying, okay, both are red, but you could have got a red and a white, or I could have got a red and a blue, or I could have got a white and a blue, or I could have got 2 whites, 2 blues, etc. You can get yourself buried down in detail, and what you want to do is get used to simplifying the situation and say, as far as you're concerned, in any urn, since I only want to know the probability of both are red, when you pick a ball, it's either a red or it's not a red. Okay, so you simplify your categories, and this is a very common idea: is simplify your categories. Just say to yourself, what's the efficient way of getting there? Now, and then B, well, that actually is a Bayes theorem question. Am I going to solve this problem right now? No, I'm not going to solve the problem right now, but I will tell you that those are the answers that I worked out. Okay. Yeah. So there's.
I will add one thing. So again, the reason we care about these kinds of problems is when you take statistics classes later on, the idea of statistics is you observe things in the real world, and then you try to learn about the environment. So you can imagine, like, urn 3 has a lot of red balls. Maybe that's like a lot of disease in the population, whereas like urn 2 doesn't have much disease at all. And then you're saying, like, if we see people with disease, what's the chance there's actually low disease in the population? This is the kind of question that you care about in stats, and that's why this kind of Bayes theorem thing is really important. It's not just to torture you. It really is learning about the universe given your observations. You observe the balls, and you try to learn which urn you're actually living in. Question over here.
I know you said that you weren't going to solve the problem. For question B,
Yep.
the chances of it being 1, wouldn't that be urn 1? Wouldn't that be 3 squared? And the chance of being urn 3 would be 7 squared. And the chance of being urn 2 would be 1 squared. So wouldn't that be 1 over 59?
So when you said 3 squared,
Yes.
3 squared. Well, it's not. You don't mean 3 squared. 3 out of 10 squared.
Oh, yes, sorry.
3 out of 10 squared. And then you said urn 2 was going to be what? 1 squared.
Yeah, I think they might be right, actually.
No, just a second. Let's just go through here. 1 squared, and urn 3 was 7 out of 10 squared. And then what did you do with those numbers? Right.
that, it'd be 59 total possibilities. And if it's asking for just urn 2, wouldn't there only be one way to pull 2 reds consecutively out of urn 2, being the 1 red and the 1 red? So wouldn't it be 1 out of 59 instead of 3 out of 59?
I better double check it, eh?
Well, in other words,
Okay.
the 59 is coming from 3 squared plus 1 squared plus 7 squared, which is indeed 59. And then I suppose if there's 59 possible things, and the 59 is 3 squared plus 1 squared plus 7 squared, it really should split up as 3 squared over 59, 1 squared over 59, and 7 squared over 59. So that makes sense to me.
I might have canceled something out wrong.
Okay.
So it says you can't trust everything. Can't trust
Very good.
everything. Work it out for yourself.
Well done. Yeah.
Good stuff.
Yeah, I think I agree. I think I'm convinced.
I think I'm convinced.
The only thing that could go
Okay.
wrong is if like one of them doesn't have 10 balls. Do they all have 10 balls?
They all have 10 balls.
Oh, okay. All right.
They all have 10
So
balls.
then I think I agree.
Okay. So on the part C and D,
job.
part C and D, again, just adds a little extra complexity here rather than 2 balls, which are both red. Now it says you're going to take 3 balls, and what's the probability of obtaining 1 ball of each color? Okay, so, well, let me just check our time here. Write down an expression for that. What is the probability of obtaining 1 ball of each color? Don't worry about working out the final number. Just work out what you think is going to give you the probability of obtaining 1 ball of each color. Just going to check. One ball of each color. Got an expression? Got an expression. You put an expression down. Write an expression down. Trying to point out the common error is not recalling that. You've got to consider the different orders.
I drew a little tree, and I got 1, 2, and 3, and then I wrote 3 out of 10 times 2 out of 10 times 5 out of 10 for the first one, because it was 3, 2, 5, then 1, 4, 5, and then 7, 1, 2. So that's the probability for each one, and then I guess we have a one-third chance on each branch, so we kind of take the average of these 3 numbers, 1/3 times this, plus 1/3 times that, plus 1/3 times this. How'd I do? Anyone get something different? Put your hand up if you got the same thing as me. Put your hand up if you got something very slightly different. Yeah, what was your slight difference? Or like the first ball should be a different color. So you're right. It's very suspicious that the first thing that happens is a 3 out of 10, whereas the first ball you pull out of the bag will definitely be fine. Like we just saw that in the example that we did before with the 3 duplicate dice rolls. The first ball is always fine. And indeed, you're onto something. There's a mistake in what I did. There's a mistake. It's not, I found the probability of something, but it's not the question that was being asked. It's not the probability of getting 1 ball of each color. I found the probability of something else. Yeah. Are you supposed to multiply by 1 over? Well, there's the 1/3 branch over here. Yes, I did that. So I wrote all three, and then you have to do 1/3 times this, plus 1/3 times this, plus 1/3 times this. So that's not the mistake. Yeah, what is the mistake? So if you look at the thing I've done 3 out of 10, 2 out of 10, 5 out of 10. This is red, white, and then blue. So I have not found the chance of getting one ball of each color. I have found the chance of first you get a red, then you get a white, then you get a blue, right? So this is the correct answer to the question, what is the probability? What is the chance to get red, then white, then blue?
But did we specify a specific order? So what have we not accounted for? Yeah.
Every other order that you can draw the ball in that one.
How many orders are there?
6.
6, right? 3 factorial orders for arranging your red, blue, and white. So the probability for what we want is each of those has got to be multiplied by 6.
So yeah,
Right?
3 factorial, which
Okay,
is 6.
so this is a very common thing, very common error is for people to forget about the different orders of doing things, okay? So that's one of the things you've really got to watch for very carefully. Okay, we said we are going to make sure. And a comment on D. If none of the 3 balls selected were red, what is the probability that urn 3 was chosen? I just want to mention that this is a bit of a hint. There's all kinds of ways that the 3 balls selected, that not all of them are red, but do we have to keep track of all those ways? We do not. As far as we're concerned, a given ball is either red or it's not red. And so we just collapse our white and blue balls into a single category of not being red. And so urn 1 contains 3 that are red, 7 which are not red, and so on. And then you can work this out. So I'm going to put these slides up with answers. I'm going to go back and double check that answer, which sounds like it's wrong for that previous one. And we're going to cut this now because there's a midterm coming in here in just a couple of minutes. Do your best getting through the probability questions this weekend. On Monday, we will discuss a couple things related to those probability questions, a couple of the harder questions.
Yeah,
Okay?
and don't forget you have mathematized homework too as well tonight if you haven't done it already.